Hi, welcome back. So we are on to magnetism and matter. So we discussed about the permanent magnets, which are basically uh, magnetic materials, in some way magnetized and available in nature. Okay, so the permanent magnets, we also discussed about how if you keep a magnet in a certain magnetic field. Let's say you have a magnetic field which is now created either by electromagnet or by a permanent magnet. There is certain magnetic field already. In a magnetic field, when you keep, let us say, a compass needle, what will happen? We studied that part. Okay, we said that if the magnetic field is there like this, and if you keep a compass needle, we saw that the compass needle actually the needle experiences a certain torque. Okay, the torque is actually kind of proportional to this angle theta. And we talked about the how do we calculate that? What is the torque? We said the torque was actually equal to m cross b, where m is magnetic moment of this and b is the magnetic field here, and the angle theta is the angle between them. So mb sine theta. So then we already also shown that just by measuring the compass needles, the time period of oscillations, when you just keep it there in front of that, how can we actually measure the B? So we found some formula for that. Now, so the one more last part that we need to see in that is that if whenever there is a certain angle that you create, okay, here theta, and keep it there. So one thing we can say is that there will be a force that will attract this and comes this side, and there is also another angle of looking at from the point of view of energy. So the least energy state is the stable state when it is aligned to the B. Okay, so when it is aligned to the B, it doesn't anymore move. There is no energy in that. There is no potential energy in that. When it is already aligned, when it is stable in equilibrium, there is no potential energy. On the other hand, if you had kept it with certain angle theta, okay, then if you know that that position has a certain potential energy in it. So that potential energy, generally we talk about potential energy in the case of a linear movements and potential energy there. We always do work done in moving from the this one reference state to this. Generally, it is a very relative term. Potential energy can be measured from any particular reference state. It's arbitrary, in the sense that, for example, when we want to measure the potential energy of this chalk piece, let us say, because of the gravitational potential energy, we always measure it from the ground. Ground we say 0, and we measure it from that. So you can measure from the table, you can measure from anywhere, and even in the 10th floor ground you can take the base. So it is all about what is the difference in the potential energy. Now, so that is by you can find out by doing the work done. Let us say you want to find out the potential energy of this with respect to the potential energy from the ground. So at the ground I will keep it, and from there I will move it up. Whatever is the work done, I will compute that, and that would be the potential energy of this. So that is our work energy theorem. So same is the case in the case of a rotational mechanics. So there also potential energy is about how much of torque you need to give to turn it that much. So we will give work done again, potential energy, let us say U. Okay, we will give potential energy in terms of U, and it is we call it as magnetic potential energy, M, is equal to work done, okay, in turning to angle theta. Okay, so that torque that you use to turn it should actually be opposite to the torque that this produces. Let us say you are turning like this. Okay, now there at every angle there is a torque that is produced by the magnet magnetic field in this direction. Okay, this is the torque produced by that, and there is a torque that you have to give in this direction to take it that side. So, if they are equal, that means there is no acceleration. Okay, and if it is already set to move, then it keeps moving slowly, infinitesimally slowly it keeps moving, no acceleration. So then in that case these two torques are equal and opposite, you have to cancel each other. So hence we can say the torque that it is used to move it is equal to this torque. Okay. So and with the angle theta. So I will say basically work done in the case of a rotational motion is torque into angle mode. Rather than force into displacement in the linear motion. Force into displacement, force equivalent is torque in the rotational motion, and displacement equivalent is displacement angle like theta. Okay, so we will say tau d theta. This is actually the why do we do this integration? Okay, so this integration we do because tau itself actually is a function of theta. Okay, we can say the tau of theta, d theta. Tau is in the sense that the torque is not common at every point of is not constant at every point of space here at this theta, at every theta torque is different. Okay, it's continuously varying like this dependent on the theta. So hence we will have to actually take the infinitesimal values and then add it at every small position. You find out what is the tau and how much the theta you varied and add that, and when you make theta tending d theta tending to 0, that means that you are doing it a continuous way, and that is called integration. Okay, so everywhere you have to get this right. Why do we use integration? So we are summing up all the work from here to here. Okay, in a continuous way. So we need integration. Tau d theta. Now you know what is tau theta, which is nothing but integral of m cross b d theta. So let's just do magnitude of that. Okay, so you can say um is equal to integral of m b sin theta d theta. This is the magnitude. Now mb sin theta is nothing but m cross b. Okay, now magnitude only I am taking. mb sin theta, if you basically integrate, it will be nothing but mb are constants. Integral of sin theta d theta, which is minus cos theta. So minus mb cos theta d theta. No d theta. So this is what we integrated, 0 to theta. So whatever angle you are taking. So now when you do like this, okay, this can be simply written as in the vector form m dot b. So there also in the linear in the electric field situation also we got it as p dot e, work done. Okay, that is dipole moment dot electric field. Here also the work done is m dot b, that is magnetic moment dot the magnetic field. Okay, this is the work energy. So at any point of time, at any point in space, when you turn it and keep it, what is its energy? You can calculate using that. Okay, so generally, and the potential energy is there even in the rotational motion and also in the translational motion. In any case, okay. So here is the rotational motion scenario. So now after having known this much, let us do one or two problems to get an idea of what we have learned. Okay. So one question you can take. The magnetic needle has magnetic moment 6.7 into 10 to the power of minus 2 ampere meters. Magnetic moment is 6.7 into 10 to the power of minus 2 ampere meter square. This is magnetic moment of a needle. And the moment of inertia I is equal to 7.5 into 10 to the power of minus 6 kg meter square. Okay, so moment of inertia is given. I is equal to 7.5 into 10 to the power of minus 6 kg per meter square, kg meter square. Okay, it performs 10 complete oscillations. So 6.7, 10 complete oscillations into 6.7 seconds. So 10 oscillations in 6.7 seconds. So T is equal to 6.7 by 10, which is equal to 0.67 seconds. So you got T, I and B, M, and we have a straightforward B's formula. B is equal to 4 pi square into moment of inertia divided by mt square. So if you substitute it, you will get the value of B, which is nothing but in this case we got it as 0.01 Tesla. So this is one question. It's a very straightforward substitution question. So just as a practice you can do it. Let's go to the second question. Okay, a short bar magnet placed with its axis at 30 degrees with external field of 800 Gauss experiences a torque of 0.016 Newton meter. So there is a short bar magnet placed with its axis 30 degrees with the external field. There is an external field B, which is 800 Gauss. So Gauss and Tesla, you should know the conversion criteria. Okay, one Gauss is 10 power minus 4 Tesla. Okay, that means 10,000 Gauss is 1 Tesla. So 30 degrees you put a bar magnet, 30 degrees. It experiences a torque of 0.016 Newton meter. So torque that it experiences 0.016 Newton meter. What is the magnetic moment of the magnet? So question is A, what is the magnetic moment? M is equal to how much? So B, what is the work done in moving it from its most stable to most unstable position? What is the work done in moving it from most stable, work done from most stable to most unstable position? What is the work done? So for that you need to know what is the most stable position, what is the most unstable position. That is C part, B part. And C, the bar magnet is replaced by solenoid. So let's go to the C part a little later. First we'll find out these two. Okay. So the A part is somewhat straightforward. What is A part? If you see, it directly is related to the equation that we have. Okay. So we'll say we know what is tau. Tau is equal to m cross b. Okay. M cross b is mb sin theta, magnitude wise. Tau is given 0.016. M is basically what we have to find out. B is given, which is 800 Gauss, 800 into 10 power minus 4 and sin 30. Okay, so that is nothing but 0.016 is equal to 800 into 0.01 10 to the power of minus 4 is 8 into 10 to the power minus 2, which is nothing but 0.08. Okay, so I'll write it as 0.08 here. Is equal to m into sin 30 is half. So m is equal to, okay. So look at this, 0.08 is nothing but, okay, 16 divided by 80 into 2. So 16 divided by 80 is 0.2. 0.2 into 2 is 0.4. This is the value of ampere meter square, m that you calculated. Okay, so that is a part A. So let's go to part B. Okay, part B is, this is A. part B, work done from most stable state to the most unstable state. Okay. What is the most stable state? Whenever it is perfectly aligned, this is the most stable state. Okay. So what is the most unstable state? So it is when it is completely opposite to this, like this. Even if you give a little like this, it will basically come back to this position. Okay. So most unstable state is nothing but 180 degrees, and most stable state is 0 degrees. Okay. So the maximum energy is always there in the most unstable state. Minimum energy is always there in the most stable state. So work done is at this state whatever energy is there. Okay. So whatever we talk about is work done is equal to potential energy at unstable state minus potential energy at stable state, which is nothing but how much? So this is so potential energy is tau dot B. Okay, which means basically we are going to say not tau dot B. So potential energy we just now calculated it as m dot B. So m into B into cos theta. So in this case basically cos 0 minus m into B into cos 180. Cos 0 is 1, cos 180 is minus 1, minus of minus 1 is 2. Okay. So this is basically 2 MB. Okay. So what is the value of m? M is 0.4 and B is how much? 0.08 Tesla. Okay. So this is 0.8 into 0.08 is nothing but 0.064 joules. That is the work done. Okay, now the last part, C part, I have not told you what is that I wanted on the C part. Okay, C is the bar magnet is replaced by a solenoid of cross section area 2 into 10 to the power of minus 4 meter square. The solenoid whose area is 2 into 10 power minus 4 meter square, and it has 1000 turns. N is equal to 1000 turns. Question is that it produces the same magnetic moment. It produces the magnetic moment of 0.4. Okay. What is the value of current? Determine the current flowing through a solenoid. I is equal to how much? So this you already know. We have a simple formula to calculate the magnetic moment for a solenoid. Solenoid is equal to M is equal to actually N into I into A. Number of turns into I into A is generally what is magnetic moment. So number of turns is basically added to that. So we know all these values. So we know that it is 0.4. We need to produce 0.4 is equal to 1000 I into A is 2 into 10 power minus 4. So from this we can actually calculate I is equal to, I think, 2 amps. Correct. So 2 amps. So 2 amps current, if you make it go through that 1000 turn coil, okay, then it will actually produce 0.4 ampere meter square as the magnetic moment. Okay. So every one of these small magnets will have a magnetic moment. See, like how we actually talk about charges. Generally, when you ask when you talk about a charge, we talk about how much is the charge. So we'll say this many coulombs. Okay. So when you talk about a magnet, I'll give you a small magnet. So what is the power of the magnet, if you ask? Okay. So the power of the magnet, whenever we say, we don't have any other thing to measure. We measure it using magnetic moment. So we say, what is the magnetic moment? So magnetic moment we calculate and we give it. Okay, so how do we calculate the magnetic moment? We can always calculate in another field. You can keep it and see basically how it turns. Okay, because it is not about one charge. Okay, if it is like a single charge, you can measure the force and you can get Coulomb's law kind of a law. Whereas here it is always, you can never find a monopole. You will always have two poles. Both of them are basically there nearby. So each one is cancelling each other's power in the near field. So it has to be the two together as a dipole you have to take. Hence, whenever we talk about a magnet, we always talk about a magnetic moment. Okay, so that is why we calculate the magnetic moment. And the equivalent of a permanent magnet, we can actually take a solenoid, and there also it can calculate. There it is straightforward. Using the current and turns, you can calculate. Okay, that is basically our question that helps you solve this question. So understand this a little bit. Now, so I'll ask you some conceptual questions, and let us see whether we know the answers to some of them. Conceptual questions. There's nothing to work it out. Okay, think and answer. The first one is, what happens if a bar magnet is cut into two pieces? What happens if you cut into two pieces? Transverse in length and along its length in either way. If you cut into two places, definitely you can say when you cut into two parts, it will give you two magnets. That is all. Okay, so you can never get a single magnet. That is all known to you. Okay, a magnetized needle in a uniform magnetic field experiences a torque, but no net force. If you put a needle in a magnetic field, okay, the needle will actually turn like this, but not the magnet itself move towards the other magnet. Like a charge, if you put in another charge field, it will move towards that. Why doesn't this happen like that? Because you can never have a monopole. You can always have dipole only. And there you can see magnetic moment and it turns. In a uniform magnetic field, it only turns. But if it is a non-uniform magnetic field, it also moves. Understand that. Okay, it's a uniform magnetic field, hence it only has a torque. Now, an iron bar near a bar magnet, however, experiences a force of attraction in addition to torque. If it is an iron bar, it experiences a force of attraction. But if it is a needle, it only turns. That is because the iron bar, okay, when it is actually put in the magnetic field, it induces inside that certain magnetism. Okay, the dipoles will be there inside. Okay, now what happens is basically the one which is nearby to this. For example, if you have a magnet here, north and south, and you put an iron here. Okay, now what really happens is this north, this is south. Let us say this is north, south, north. This is how it induces. It induces a certain magnetism inside that. Okay, like how charge induction happens. So how it induces inside this, that we will study a little later in the same chapter. So now when it induces that, you can see that this north pulls this side. Okay, whereas this north pulls this north outside, this side. So this north actually is pulling the south and pushing the north. If these two are equal, then it will stay there. Okay, it will not come. But these two are not equal. Why are they not equal? Because south is more nearer to this. Hence, the force with which it pulls is higher than the force with which it pushes. So the net force is towards this. Hence, the iron actually comes towards it. Okay. Then, so must every magnetic configuration have a south pole and a north pole? Okay, what about the field due to a toroid? So look at this actually. Okay, if you have a toroid, we studied a toroid. So and we wound it like this. This is the winding of a toroid, and we saw the magnetic field inside that is like this, circular field. like this. So where is the North Pole, where is the South Pole, you can ask. Okay. So whereas in the case of all other things we have seen South Pole and North Pole. So the only thing is, so this has to be South Pole and North Pole if there is a non-zero magnetic moment. That means if you calculate the magnetic moment, that is the power of it, okay, magnetic moment what we say, if it is non-zero, if it is not zero, then it must have a North Pole and South Pole. Okay. Whereas in this case you can see that its magnetic moment is actually zero, though there is a magnetic field here. Hence, it doesn't require it to have a North Pole and South Pole in the case of a toroid. Okay. And in the case of a, if you take for example a straight line, a solenoid, okay, take a solenoid like this, solenoid. In the case of a solenoid, can we have just like this magnetic field? So towards the end actually, you know, solenoid generally have it like this. Like this. So we will have actually in this case north and south solenoid. Okay. So whereas in the case of a toroid only it is not there. So two identical looking bars A and B are given, one of which is definitely known to be magnetized. We do not know which one. Okay. How would you ascertain whether or not both are magnetized? If only one is magnetized, how does one ascertain which one? Interesting. So you are given two bars. Okay. So both the bars actually are looking exactly alike. One of them is magnetized, another one is not. Okay. Iron though. Now, how do you find out that whether both are magnetized or only one is magnetized? That is the first question. Now, that is very straightforward. Why? If you actually had both of them magnetized, if you have both of them magnetized, okay, if you bring it near, they get attracted like this. Okay, fine. Even if magnet it is attracted, but if you put it in the other direction, if you bring it near, they will be pushed. You can't just put it on the top of it. They just are pushing. I'm trying to put it. It is not. It is getting pushed. Okay. So this basically repulsion. So repulsion is a sure sign saying that it is magnet. It is a magnet. Okay. Now then you can ask a question: which one is actually real magnet and which one is not? So you know, once you know, find out that both are magnets, no need to answer the second question. If one of them is actually magnet and another one is not, what will you do? You just suspend it in the air and see which one turns north south. So that one is magnet, the other one is not. Simple. Okay. So the other important point also is let's look at only one last part, two more questions we will try to answer. Okay. What is the magnitude of a equatorial and axial fields due to a bar magnet of length 5 centimeters? Write down. What is the magnitude of equatorial and axial fields due to a bar magnet of length 5 centimeters? Bar magnet length we call 2L, 5 centimeters. At a distance of 50 centimeters from its midpoint. So R we say is 50 centimeters. from its midpoint. So what we need to find out is the B. We have to find out B. So we have to find out B at two places: B axial, B equatorial. Okay, the magnetic moment of the bar magnet is 0.4 ampere meters. So magnetic moment is given as 0.4 ampere meter square. Okay, so now it's just you have a bar magnet of length 2L, 5 centimeters. So now this is along the axis. Somewhere here I want to find out B, which is B axial. Somewhere along this we find out B, this is B equatorial. Okay, so distance is given as 50 centimeters. 50 centimeters. This is also 50 centimeters. So how do you do that? Straightforward. Okay, the formula that you are going to use is mu naught B equatorial is mu naught into m divided by 4 pi r square, 4 pi r cube. Always dipole moments are all r cubes. Okay, so you can give the values basically and compute. You will get basically this one as 3.2 into 10 to the power of -7 Tesla. The answer. Just substitute it values. So the other one axial is equal to mu into 2m divided by 4 pi r cube. That will be double this, 6.4 into 10 to the power -7 Tesla. Okay. Next one. Next one is basically, let's try to understand the picture given. So let's do one thing. This example of 5.5 we will do it in the live class. Let us move on to magnetism and Gauss law. Okay, what is magnetism and Gauss law? So magnetism and Gauss law. You all know what is Gauss law. In electric field, what was the Gauss law? If you actually had an electric field somewhere, okay, so let's say I have a charge and the charge gives rise to certain electric field like this. Now if you take any surface, okay, surface means not just a circle, I am talking about the full sphere, and over which if we basically look at the flux is nothing but E dot ds delta s. If we basically take it over all surface, full surface, okay, that would be equal to the charge enclosed, which is q divided by epsilon naught. So you would actually think that in the case of a magnetism also same thing is true, but in the magnetism the problem is this. Okay, wherever you go, there is no end to these lines. So if you take a either a solenoid or a magnet, okay, so if you take that, even a magnet or a solenoid, the lines actually go like this. These are our B lines. So this is coming this way. So the lines are actually always loops. Lines are always loops. They start from one end and come back to that only. There is no way there is a starting and ending point for the lines. Because of that, what happens is, assume that you will take a certain surface, a certain sphere here, like a small sphere kind of thing, a surface, full surface, okay, and you find out basically the B over the whole thing. So that means I want to find out sigma of B dot delta S. I want to do that. Okay, that means basically what? I take the B on the surface, okay, and I will look at the vertical component of the B only, okay, in the sense that perpendicular component of the B. So at every point basically I will, let us say if there is a sphere like this, at some point B is in this direction, okay, I will take only I'll split into two components, one like this, one like this. Only this component I will take. Okay, so that is the meaning actually of B dot delta S, because delta S is an area of a small area here. Okay, and this area, when you look at the area is given by a vector which is perpendicular to this. So area vector is like this. Area vector is like this, and B vector is like this. Okay, then B dot ds means B into ds into cos 0 is 1. Okay, so if it is some other angle, we take actually the theta. B dot ds means this is in the direction of delta s, this is the direction of B. B dot delta s means B into delta s into cos theta. So we take it all over and add it all of them. When you add all of them, you will actually always get 0. Why do you always get 0? Because, only because, okay, the number of lines which are going out of this, okay, going out of this is equal to the number of lines which are coming inside this. Because all the lines actually pass through, there is no line which starts or ends anywhere. So hence any small closed area surface you take, the number of lines which enter that surface is equal to the number of lines that go out. Okay, and then you finally add up all the things, you will always get 0 only. So the Gauss law of magnetism, Gauss law of magnetism states that, so a simple statement of Gauss law of magnetism is nothing but the net magnetic flux through any closed surface is 0. The net magnetic flux through any closed surface is 0. That is the rule. Okay, B dot delta S sigma for all S is equal to 0. Remember this always. So in the case of a magnetic field, this is always true. Okay. So that is basically our understanding of the Gauss law. Okay. Now, so so we will have to do some more experiments and problems to get a better hang of what these things mean. Unless you apply it, it will not basically stick in your head. So let us do those things in the exercise where we work out during the live sessions. So now we will move on to basically another most important part of our discussion. Okay, that is basically about Earth's magnetic field. So Earth has a magnetic field. How to deal with Earth's magnetic field? Let's look at that. Okay. Let's say let us take a scenario of, now we will talk about Earth's magnetic field. So if you take a, for example, scenario of an Earth, okay, this is my Earth, assume a sphere. This side is, let us say, north, south. So how does the magnetic field look like in the case of Earth's magnetic field? Okay. Let's see that. In the case of the Earth magnetic field looks something like this. So in the sense that you can clearly see that the magnetic fields of lines actually enter through this and go out of this. Unlike a normal magnet, okay, if I take a normal magnet, the magnetic fields of lines exit through this and enter through, this is N, this is south. So only here, in all the bar magnets or any magnet you take, it exits out of the N and gets inside through S. Only in Earth's magnetic field it actually enters through this and gets away from this, and it is covered in overall everywhere around Earth. The Earth's magnetic field is very strong near the poles, and it is slightly weak around everywhere. Okay, so that is the picture of the Earth's magnetic field that you can see. Now, let us look at the magnetic field from the point of view of how it actually looks like. So if you see, this is what is the real scenario. Okay. It is entering inside the air. Look at this arrow. This arrow is like this. This arrow is outside. So entering from north. And so why is that so? It is very simple. The reason is that we called, okay, whenever we put a compass needle, and if the compass needle turns towards this side, the north of the compass needle, that we call north. That is all. Okay, it is our convention. We called it this one north. This is our geographic north, or a true north actually. Okay, north. So, and this is south. And the thing is that internally, really speaking, this side we have south pole, and this side we have north pole of the internal magnet. Internal magnet has here south pole and here north pole, but we don't want to call it like that. Earlier we used to call it, it's just confusing. Okay, north is south, south is north, all sorts of confusions will happen. It is just a convention, no need to worry. Call this normally as geographic north, geographic south, and call the other one as magnetic north, magnetic south. On the top only you call it as magnetic north, down only you call it as magnetic south. So it's just that whenever we say magnetic north of the earth, we mean wherever the compass needle north points to is called magnetic north. It is not about the north pole of the magnet situated inside. The definition is like that. Wherever the compass needle is pointing to, that is the geographic, that is called a magnetic north. So now this magnetic north and geographic north, are they both same? They are slightly away from each other, in the sense that internally whatever generates magnetism, okay, is not perfectly symmetrical with respect to our geographical north-south axis. It is slightly different. So it is slightly offsetted. Magnetic north and geographic north are not exactly at the same point. Okay, in fact, if you see the way the theory of generation of Earth's magnetic field, if you cut the Earth and see, okay, generally earlier it was believed that there was a huge bar magnet inside the Earth. Hence, Earth actually is magnetic. But later that was all basically proved wrong because of the temperatures inside. Nothing can stay as a large bar magnet like solid. It's all liquid inside. Okay, it's such high pressure and temperatures, and that liquid actually is running around inside. The inner Earth core is there, around which the liquid is running. Okay, this pressure is such that this is all liquid lava, and there are a lot of ionized gases. Ionized liquid actually going here. And because of the Earth's rotation, this ionized liquid also will rotate, okay, in the opposite direction. Okay, if Earth rotates like this, liquid rotates with respect to that in the opposite direction, mainly because of the inertia, rotational inertia. So when it rotates like that, that means that this is constitutes some kind of a current, isn't it? This is some kind of a current. So whenever there is a current flow in a loop, we know very well that that will give rise to a magnet, a magnetic moment. Any current will give rise to a magnetic field. Okay, so it will produce a certain imaginary magnet like this. This current will produce an imaginary magnet. This is no real hard magnet. It is it's a magnetic kind of, it's a dipole that it has produced, long one. So that is how Earth actually is a magnet. It is because of this. That is today's theory. It's because of molten material here is rotating. So this is, we also found out that this is kind of true. For example, if you go to moon, there is no such material. Okay, moon does not have it liquid like that. So it doesn't. Moon is not having a magnetic field, and since moon is not having a magnetic field, there is also a lot of solar things which are not solar ions that come from there. So they will not get diverted. We have a magnetic field, and hence what happens is any radiations which come will actually get diverted. So now if you actually carefully watch this the sphere, the Earth as a sphere, if you see, okay, and I am just basically bending the sphere a little bit like this, okay, to the tilted like this, just to show that this is north, the geographical north, and from here if you come a little bit this side, okay, this is actually, it's somewhere in the top of the Canada, you have the magnetic north. Similarly down here there is a geographic south and a magnetic south somewhere here, the back side. So there is a slight shift at the point of magnetic north and magnetic south, in the sense that magnetism that produces north-south, wherever you see the maximum amount of field lines going inside, that is the magnetic north. So magnetic north is not exactly at the same position, the slightly different position. You can actually figure out how far it is away, and look at the globe, you get an idea. Okay, some distance away. Now, so what we do is actually we have to figure out generally what is the amount of magnetic field. That will help in many different things. We want to measure the Earth's magnetic field, and how do you do that? You have to specify the Earth's magnetic field in various scenarios, in a various numbers. So suppose if you say this is my Earth, okay, and there is a magnetic field like this, let us say. Yeah. So this is a magnetic field like this, okay, sorry, like this. At any point on the surface of the Earth, let us say here somewhere, if you stand and see, you want to measure the magnetic field, it will be seen in this direction, correct? So what do we want to specify when we say this is the magnetic field that I measure? So we have to specify a few things, that is, one, its length, that means how much is the magnetic field, how many Tesla, okay. Then you have to also specify the angle, okay. The angle here is a 3D scenario, okay. You have to also specify exactly what is the angle with respect to what, how are you going to specify all this basically, to get a, without confusion, to clearly understand, use 3 different parameters, right, to specify Earth's magnetic field. What are these 3 different parameters, and how do we use them to find out exact value of the Earth's magnetic field? Let us see that, okay. So the first one is basically like this, okay. Now you take, for example, this is our north pole, geographic north pole, like this. If I draw a line, this shows basically the north-south, geographic north-south line, okay. And this shows here is the we call it as a geographic meridian, okay. This is a line, well, I am showing you a line, okay, but actually if you cut it like this and see from this side, it is a circle. So geographic meridian is a circle, okay. And similarly, if you cut it like this here, so this is basically your magnetic north pole. So if you cut it here, this will give you actually another circle, which we call as a magnetic meridian, okay. Geographic meridian and magnetic meridian. We can actually do like that in both the 2 circles we will get, okay. Now we will now find out, we want to find out, this is the global view. Now we want to find out and go to a specific local point and see how we can find out the magnetic field at that point. Okay. So how do we measure? We measure it using basically a few parameters. First one is called as declination. So how do we do this declination? Declination is an angle between basically true north-south and the meridian north-south, magnetic meridian north-south, okay, as measured from the point at which you want to measure the magnetic field. So how does it change? Let us see. Okay. Now I want to basically measure at this point. At this point, I want to measure, okay, what is the declination. So what will I do? I first draw one circle. Okay, I will draw a geographic meridian passing through this point. I will draw a circle. I'll cut it correctly like this. See, what I did was I took and cut it like this, okay, at the point here, passing through the North Pole, actual North Pole, and going here and passing through the actual South Pole, that is true South Pole, which is on the other side. Okay, this is on my side here, and this dotted line is on the other side. So this is how I basically cut it. Okay, this is called, this line actually is called is geographical north line. Okay. Now, if suppose the magnetic meridian was also in the same, if magnetic pole was, magnetic north pole was also here only, then if I put a compass needle on the top of this, if I put a compass needle, okay, on the top of this here, like this compass needle, it would show actually an arrow like this. See this? This is the arrow. It would show an arrow. It should show in this direction, compass needle. Okay, but actually what happens is it would show like this. Okay, this direction. Can you see this? But in reality, it cannot show like that, because magnetic north pole is not this. This is the geographic north pole. Magnetic north pole is here, little away. So then what happens is, this actually will show now, we will actually draw, okay, one line, another meridian, okay, which is magnetic meridian passing through the magnetic north pole. We will draw another circle, cut it like another circle, like this, passing through my point, joining these two to the magnetic pole, and make it a circle. Fully cut it like this. So 3D visualization, that's very important. Okay. Now once you do that, now you can see that actually this is the direction in which it shows. At that direction, it actually turns. If I keep it here, it actually turns towards this point. Now that is by that point, basically the angle between the point, when you say the angle between what is true north and what is magnetic north, this angle, okay, we call declination. So you can specify the declination at your point. So you know what is true north, okay, from your geography, you know what is true north, and you know, let us say, you can specify, let us say, the declination. Declination you can specify. Then what happens is that, so declination is a very useful thing. If you know my declination is 2 degrees, assume that you know my declination is 2 degrees. Okay. Then what does it mean? It means that I will look at my compass needle, and whatever north it is showing, okay, I will actually go offset by 2 degrees and say that is my real geographic north. My latitudes and longitudes are actually in that direction. Okay, that I will know. For the travel, that is very, very important. Okay, so but in some places the value of that is very small. Okay, like for example, if you take any line, okay, joining these two, like for example, if you take, okay, any line joining these 2 points. So let's say if I join these 2 points and draw some kind of a circle on that line, wherever you go and put your needle, okay, it will show like this only. So your declination will be 0 on that line. Okay, very clearly you can see. But other lines, wherever you go, other places declination will be there. For example, on our in Delhi, if you take it, it's almost 0. Like it's few seconds, it's few minutes, not degrees. So it's very near to 0 in Delhi. Okay, we can almost show true north. So other places not like that. Just if you go here, for example, if you are going very near somewhere here, okay, then you can see the line joining these two and these two. It's a huge angle. In fact, if you are here, okay, on the on your if you are on your equator, okay, so from there if you see, this angle is actually much less when compared to going here. So generally when you are more near to the equator, you will actually have lesser declination. More and more if you go near towards the pole, it keeps increasing. Declination keeps increasing if you go nearer and nearer. Okay, so that is called declination. So now let us look at, basically you got an idea. So declination is one angle. Okay. So that will tell you that which direction it is looking at. Now the second one is called as a dip. So what is a dip? So dip actually is, if you, instead of keeping the compass needle horizontal, you keep it vertical like this. You take a compass needle and keep it vertical like this. Okay. When you keep a compass needle vertical, okay, what happens? Let us see. Okay, first thing that you have to do is, you can't keep it vertical, okay, in any direction. That is not allowed. Okay, first of all you have to take it and align it to north south, and then keep it vertical. You cannot keep it vertical in south east west direction, it will not work. You have to first align it to magnetic meridian. So align that to magnetic meridian, okay, and then keep it vertical. So your plane should be in the magnetic meridian plane. Okay, the plane of the vertical plane should be in the magnetic meridian plane. Then only our dip works. Okay, dip is also called inclination. Now what happens is, suddenly you can see that instead of standing horizontal, it dips a little bit. This angle of how much it has dipped, okay, is called as angle of dip or inclination. So why does it dip? So if you think about it, why does it dip? Okay, you see that in a case of a spherical scenario, if you are actually there on your sphere somewhere here standing, and you are putting it standing here, and in the meridian if you put it like this horizontal, okay, this is horizontal, so you stand like this, you are standing like this, correct? If you are standing like this, what is horizontal to you? This is horizontal, this is north, this is south. So imagine properly, this is horizontal, it's not vertical. Okay. So if you are standing like this is horizontal for you, and in this horizontal you see this is north, this is south. So north is attracted to the north. This is because inside it is actually south, so we still call it north. Okay, so it is attracted this side, south is attracted this side, and they are both equidistant from the poles, and hence you can see that it is horizontal. So it is one way of looking at it. Okay, the other way is to say that if you draw these lines the direction of the magnetic field is like this. So it is aligning with the direction of the magnetic field. We know that whenever you keep a needle, compass needle, it always turns towards the magnetic field. It shows the magnetic field. Torque, otherwise it's the stable position. If you are in any other position, it will have a torque. Okay. So if you actually keep a magnet, something in the vertical, see, look at what I am doing is I am keeping it in a such a way that the axis of rotation here you can see is horizontal and it can rotate in a vertical plane. That's how I have kept here. Okay. So this is my this whole thing, you turn it around like this and keep it. Okay. So it is in the vertical plane. So in the vertical plane on the equator, if you go and put it here, this actually shows exactly horizontal like this. That is because this side and this side, both of them are pulled by N and S in equal distances. On the other hand, if I put it somewhere here, so I will put it as, let's say there is one more. Okay, so this is the lines of force, the lines, field lines. So here if I put it, okay, you can see that it is aligned to this, which is not actually horizontal. So the horizontal, this is more attraction towards the north, okay, and less attraction towards the south. So in the sense that one of the things is dipping like this, it is showing the north pole. When you go more and more towards the north pole, it has to dip more and more. And in fact, if you stand on the magnetic north, okay, I am writing here, let us say this is magnetic north itself. If you stand on the magnetic north, then suddenly the dip will be 90 degrees. It will show like this completely, because it is showing the pole. Okay, this angle is called as the dip or inclination. Always whenever you are measuring the dip, you have to allow the needle to swing in a vertical plane and align that plane to the magnetic meridian and then do your work. So think about this, no? It's not very easy. You always get to mistake it. Okay. So very carefully understand what this dip is. So first angle that we have specified is declination. Second angle we have specified is inclination or dip. So these two angles, plus if you specify one more parameter, you would have specified everything about the magnetic field at any point. What is the other parameter? The other parameter is the magnitude. These two are the angles. So what is the magnitude? Let us see. Okay. Now look at this picture. Okay, we have made it very abstract picture. Let's say this is my needle. So needle is standing like this. This is my true north. Okay. And actually declination will tell you from true north to the magnetic north what is the angle. This is magnetic north. So if you have kept a horizontal needle, magnetic compass needle, it would have turned like this to the magnetic north. That angle is called declination. That is specified to you already. And then if you keep it in the vertical plane like this, on this line is the basically magnetic meridian. In this plane, if you keep so that it can move in the vertical plane, it would dip like this because of the field direction, and that is the dip or inclination I. Okay. So you have two angles, D and I, dip and inclination, declination and inclination. Okay. And if you are given one more information, which is horizontal component of the Earth's magnetic field. Okay, what is the horizontal component of the Earth's magnetic field? So horizontal component is simply nothing but, if you take this point, okay, and draw a parallelogram here. This is the horizontal component H, this is the vertical component Z. So horizontal component and vertical component. So if you know both horizontal and vertical component, you know F. Okay, we don't know F generally. So if you are given a horizontal component, if we somehow find out the horizontal component H, and if we know the value of declination, and if we know the value of inclination, we can compute if we know these three things, we can compute f, vector f, isn't it? Think about it. How do we compute? Okay, so we can compute because we can write down like this. Okay, first thing that we can write down is so you know z is equal to our total b, okay, full component, let us say, into sine I, whereas h is equal to b cos I. So if you actually find out, if you know I and h, you can always find out b. Okay. So tan I is equal to z by h. So just by these angles, we can calculate. Okay, in the sense that given some of these things, you already know how to resolve the vectors. So using that, given these three values, you can compute exact value of field. So if you do one or two problems, I think you will get a better idea of how to do that. Okay. So I will actually do only one problem. So take down one problem. In the magnetic meridian of a certain plane, the horizontal component of the Earth's magnetic field is 0.26 Gauss. Okay, horizontal component is given as 0.26 Gauss. H is equal to H magnetic field is equal to 0.26 Gauss. So it is in the magnetic meridian. So we have seen that it is in this magnetic meridian. On this line, this H is given to you. And the dip angle is 60 degrees. I is equal to 60 degrees. What is the magnetic field of the Earth at this location? So what is the magnetic field B at this location? B is equal to, okay, so we know that B cos I is equal to H, or B is equal to H by cos I. So H is given 0.26 G. Cos I is cos 60 is half. So this is 2 into 0.26 is 0.52 Gauss. Okay, from there we can find out basically true north where it is. So if it is needed from our declination. Okay. So I am going to basically end this session at this point because we have covered a lot in this session. So the next one we are going to talk about is magnetization of a certain materials. How do you magnetize something? How do you measure the magnetization, amount of magnetization? All that in the next session. Thank you.